This video will cover how we are going to model the effects of thermal radiation on the balloon system and what you can do as the designers to still meet the objectives. Now these are junior level thermodynamics and heat transfer concepts, but I'm going to give you a high level intro to the subject area as it applies to our balloon design. First, it'll help to remind ourselves what happened during the scale model experiment when the neutrally buoyant balloon was placed in front of the heater. The heater transferred energy into the balloon system. This increase of energy caused the lifting gas temperature to rise, which resulted in a larger occupied volume of the gas because the balloon shell expanded to stay consistent with our zero pressure gradient assumption. We can put some theoretical backing to this observation. Recalling the ideal gas law, PV equals nRT, of course R will stay the same, and as long as we don't lose any lifting gas, the number of moles, N, remains constant. So if temperature increases, so does the quantity PV. This means either pressure increases, volume increases, or both increase. For our scale model balloon, the pressure should stay approximately the same, and in fact it will stay the same if we assume a zero pressure gradient balloon, as the surrounding pressure remains the same. This means the only variable that can increase is the volume. Now we can also think in terms of density. If the mass stays the same, but the volume increases, then the density of the gas must go down. And if the overall mass of the system stays the same, but the occupied volume is now greater, then the overall density of the system also goes down. It is because of this decrease in density of the entire system that the entire system is now positively buoyant because it has a lower density than the surrounding fluid. So it increases in altitude until it reaches a point in the fluid that has the same density. We apply this exact same reasoning to the large scale balloon, but instead of a little plug-in heater, we'll use the largest, most powerful, most awesomest heater in the entire solar system. The object that gives you sunburns when you spend too much time on the beach or skiing during a bluebird day. The sun. And instead of just holding the large scale balloon still until it heats up, then releasing it to see what happens, we're going to predict the response using some thermodynamics. Now before we predict the response, a few terms need to be defined. The first term is a black body. This is essentially an ideal radiator, and the emitted radiative energy from the body is perfectly captured by its surface absolute temperature and a constant known as the Stefan-Boltzmann constant. Real surfaces radiate less than a black body, and that factor is termed the emissivity. Likewise, the absorptivity is a factor that determines how much irradiated energy is absorbed by the body. The irradiated energy is the energy apparent on the surface. In reality, the values are dependent on a lot of things: material, coating of the material, wavelength of the energy, etc., etc., etc. And you'll cover these things more in junior level, as things can get really complicated. But to save you some time and effort and let you focus on the bigger picture concepts, I'm going to provide you some values that you can use that are approximate to the range of materials that are relevant for our design. We're also conducting a preliminary design analysis, so it's perfectly acceptable if our values aren't completely correct. A more detailed design analysis would seek to improve those estimates in order to give better confidence in the prediction. Now, if you are able to find values for your specific material, then you are welcome to use them. But please, please, please do not spend much time looking for better values. That isn't the point of this exercise, and I don't want you to lose sight of the forest through the trees, as the saying goes. So now that we're familiar with the terms absorptivity and emissivity, we can look at some equations. Now you'll cover where these equations come from in junior year thermodynamics. What this diagram shows is that we have some rate of energy transfer by heat, termed Q dot, coming into our system from the sun and from the earth, and some Q dot leaving the system. Now these equations provided here are using some terms to be mathematically precise, but intuitively all we have is some energy coming in and some energy leaving the system. What we are interested in is how that energy transfer relates to the temperature of the balloon. If we look closely at this relationship, we can think that at some temperature, the balloon will be radiating energy away at the same rate the energy is coming in if the temperature of the balloon is allowed to increase enough to balance the equation. So if we set the sum of all the Q dots equal to 0, we'll arrive at the temperature that corresponds to this equilibrium temperature based on radiation. Now keep in mind the sign convention of positive or negative depending on if the heat is coming into or going out of the system. Now this assumption is ignoring the other two primary heat transfer methods that you may have heard about, conduction and convection. But the air at the altitude that we're dealing with is so thin that we can assume those transfer methods are negligible. So if we allow the balloon to reach equilibrium based on the Q in and Q out for the nighttime and the daytime, you can determine the new temperature of the entire system. For completeness, we also must assume the lifting gas temperature is the same as the entire system temperature, which is a valid assumption since we've stated the entire system is at thermal equilibrium. And from here you can proceed in a similar fashion as to what you observed with the scale model experiment. Namely, once the balloon heats up, reaches equilibrium, it will be released from the current altitude. The now larger but less dense system will go to a new altitude based on the density. A quick explanation of the variables. The sigma SB is a Stefan-Boltzmann constant with the value in units listed here. The alpha little sb indicates the absorptivity of the sun balloon system with an approximate value of 0.6. The emissivity B indicates the emissivity of the balloon with a value of 0.8. And the alpha EB represents the absorptivity of the Earth balloon system. The little q sun is the solar constant known as solar irradiance, and is the power per unit area received from the sun in the form of electromagnetic radiation. The little qe is the irradiance from the Earth onto the balloon system. Now you may be thinking that what we are assuming here is a bit counterintuitive, but it's a fair approximation for reality given the primary learning objectives of this assignment. More specifically, it isn't intuitive to think that the balloon will stay completely stationary until it is fully heated and then immediately go up to a new altitude. The real system would heat up a little bit, which would result in a larger displaced volume, go to a new altitude based on the new density, heat up a bit more as it expands, resulting in a new density, and then going to a new altitude, etc., etc. Also, the radiative heat transfer won't result in an immediate temperature increase of the gas. These effects are quite a bit more complicated to model, so we're going to make the assumptions that the entire process happens at quasi-equilibrium. You are welcome to attempt the more complicated approach if you'd like, or you can even attempt to simply iterate on the approach mentioned here a few times, but I'm confident that you will ultimately arrive at a similar result in terms of altitude. And that's what really matters for this design problem. So then what if your new altitude is outside the performance requirements? Well, that's a really good question, and I don't want to give away the answer here, but I encourage you to look back at your derived expression for neutral buoyancy and ask yourself what parameters could be changed in order to increase or decrease the balloon's altitude. Now for this project, you won't have to design the system to control the altitude, but you should be able to quantify the primary aspects of the design. For example, if you elect to drop ballast, you don't have to determine how the ballast will be dropped, but you do need to be able to say how much ballast would drop and approximately what time of day. Likewise, if you elect to vent lifting gas, you should be able to say how much gas you'd need to vent to meet the objectives. Also keep in mind that there are no constraints on what time of day the balloon arrives at the desired altitude, only that it needs to stay in residence for a minimum of 24 hours. Okay, looking ahead. Now there's only a few more weeks left on this lab. Right now, you've been exposed to all the technical material to fully complete the design. A document detailing the presentation has been posted to Canvas. This document is based on the PDR Preliminary Design Review presentation assignment that is given to seniors in the Capstone project course. And in fact, this was just assigned to them the other day. Next week, I'll go over showing you one way to insert professional looking equations into your presentation, and how to make the presentation plots look more professional. I'll also cover some presentation tips, as well as go over the specific things that we'll be looking for in your upcoming presentation. And then those will be the last videos that I'll post on this lab assignment. Until then, keep floating along with this balloon design and please reach out with questions. Thank you.